Let's get started. My name is Rebecca Parsons. I'm the Chief Technology Officer for ThoughtWorks, and I want to give you a little history lesson on evolutionary architecture. And when I first started working with Agile methods, Agile was a dirty word, and people would think evolutionary architecture was borderline professional irresponsibility, if not well over the border. And what I've found in the last few years is that that is changing. And so I want to take you through a little bit about how we got to the point where now it's okay to talk about something radical like evolutionary architecture. So first we got to define some terms. First off, what do I mean by architecture? Because even if you're writing a simple app just for yourself, you're still doing architecture. Maybe it's not the same architecture that you hope your bank is doing when it's protecting your bank account details and your access to funds, but you're still doing architecture. And architecture means many different things. One of Martin Fowler's favorite definitions for architecture is it's whatever the company thinks is hardest or most important to them. So if you're running a high volume trading application, you're probably going to be very concerned about throughput and performance. One of the early projects I did working for ThoughtWorks was for what we called a trading company. However, they didn't care about that low latency, high performance, because they only did, in their wildest dreams, 200 transactions a day. Not a minute, not an hour, a day. But each one of those transactions was worth billions, with a B, of US dollars. And so what they cared about was not performance, they cared about data security. They cared about message delivery. They wanted to know exactly where all of their data was at any given point in time, because every one of those transactions was worth so much money. So architecture might be a security architecture or a data model, or how your applications communicate with each other. It might be your technical stack. It might be your network topology. It might be how you think about things like communication and collaboration between the components. It might be all of these different things. That's what architecture is. And that's part of what makes architecture so difficult to say you're doing, because what does it really mean to do architecture? So if that's the breadth of what I'm talking about with architecture, what in the world then is evolutionary architecture? And I'm giving a talk this afternoon that will go into this in a little more detail, but basically this notion of evolutionary architecture, which means simply that these architectural components are as easy to change as they possibly can be. Another definition of architecture you might hear is architecture is the stuff that's hard to change. Well, the techniques that I'm going to talk to you about and how they evolved are designed to make it easier to change the things that are supposedly hard to change. So that's really all evolutionary architecture is about. It's how are we going to address the problem of changing these fundamental components. Maybe it's changing out your technology stack. Maybe it's changing up your application architecture or your object model. Maybe it's changing your database. Maybe it's changing out a product that you've relied on for years and putting a different one in its place. All of those things, they all involve code, but there are all also architectural decisions. So in the beginning, it used to be computing was very simple. You had a big blue IBM machine, and it ran an operating system, and people got all excited at the prospect of things like hierarchical directory structures. Wow, and oh, you can run two things at once, and it'll switch between them. Isn't that wonderful? And then there was this radical new thing, a database, because it used to be when you ran a process, a traditional business application would write records into a file. And the method of communication from one of these programs to another was a file. So you would have to go through and process every single record and dump it into a file, and then the whole file was passed to the next thing. And so even though obviously these things are different They're independent of each other because you write one, then go back and start on the next one. You couldn't do anything else because those records were coupled. The technology that we had available to us at that time meant that those things were coupled. Even though logically they weren't, even though there was no reason you couldn't run all of those things at the same time, you didn't have the technology. And that was one of the radical things that actual database technology did, was allow you to say, oh wow, I don't have to have these things coupled in that way anymore. And many people will tell you that one of the most important issues that you deal with in architecture is getting your coupling right, because some things have to be coupled. If I am sending a message to an application, that application has to be able to understand that message. We have to be coupled. There's no way that it can just figure out what I want and what I mean unless we have some coupling that is associated with that. But in general, the architectural choices that we make, we want to limit coupling to the things that have to happen. Because as soon as you're coupled, now you've limited your ability to change. You've limited your degrees of freedom. Unfortunately, a lot of the things that we know about our architecture, and unfortunately as well, a lot of the people who are called chief architects at the moment, started their careers back before fire was invented, and we had these big mainframe machines, and maybe we had this radical new thing called a database. But our technology stack is completely different. We have as standard things that you only dreamed of when many of the architectural principles that are held dear were developed. And that's what we have to start changing and fighting against. And what I'm finding is people are starting to understand that architecture, A, is important. It does not have to be stifling. It does not have to be something that limits the creativity of a development team. It can be something that actually allows for business agility, that allows for rapid code development, for all the experimentation, lean enterprise, all of that stuff. Architecture can facilitate that when it's done right. So, where did this start? In many ways, this started with the Agile Manifesto. And when that group of people got together in Snowbird and started to try to unify all of these different approaches, there were several things that came out of that that are important for what we're talking about today. Simplicity, empowering teams, rapid feedback. When you look at some of those other disciplines as well, and you start looking at XP, for example, you have lots of automation. But fundamentally, what we started with here was the notion that, yes, we want to empower teams to make the best decisions possible, and that will make those teams as productive as possible. Now, that ran counter to what a lot of architects thought their job was. I've run into architects who would say that their job was to stamp out any creativity being displayed by the development team. Well, obviously, that's going to run completely counter to what an Agile team is trying to do when you're empowering your team. But there is also a balance. We don't want to have 13 different XML parsing libraries just because each guy wants to use the one that they're most familiar with. Standards are not inherently evil. You do have to have some level of standardization for teams to be able to function, and particularly for enterprises to be able to function. And so what we started with this idea about Agile is that you no longer had to design everything up front. You no longer had to know what your object model and your database schema was going to look like before you started writing a line of code. And that was a really radical idea, because at that time, an architect's job was often sitting off in a corner somewhere, drawing out the specification for an application and the object hierarchy and all the method names and all the classes and all of that, and giving it to what was effectively a coder. Developers didn't think for themselves. They translated some specification into code, and that specification was actually pretty detailed. And it was really a translation exercise. And this all started changing as Agile started to become more mainstream. And one of the first things that we started happening is we started saying, okay, let's say how we can break down this functionality into things that we can develop more rapidly. Let's start with something very simple and then grow it. Rather than deciding in advance all of the possible features I might want to develop, let's start with something simple. Maybe it's a happy path through the application. Maybe it's dealing with one type of process. And then I'm going to start adding to that. And my code is going to evolve. And that's where this notion of emergent design came from. And we had things like design patterns that allowed you to say, okay, well, I see the characteristics of this broad kind of problem, so I'm going to use this design pattern. And you had the notion of refactoring. And even though that's one of the more abused terms in our field, what refactoring is relatively simple. You have a behavior maintaining small change. Behavior maintaining, I'm going to extract a method, I'm going to rename, I'm going to do something. And so this notion of emergent design, often done in conjunction with test-driven development, refactorings, patterns, that became the cycle of development. But in order to make this thing a safe thing to do, we also needed to make sure of two things. First, we needed to make sure that we had enough tests in there, that we knew, in fact, that these changes that we were making weren't changing the behavior in ways that were unexpected. Obviously, if we're changing code, we expect something to change, but we want to make sure that we know what that is. Another critical part, though, of doing XP and doing Agile is continuous integration. And continuous integration is not just having a build server. Continuous integration means that you're checking in multiple times a day. And if you're going to check in multiple times a day and run builds, that means they have to run fast and you have to have tests. And so what we had in this first wave was the ability at a code level to do some architectural changes. You could upend your object hierarchy if you had a good enough safety net. And in fact, I've been on projects where that was done, where we had to actually change the top-level relationships in our object hierarchy, and that was done by 2 pairs in 1 week across a 750,000 line application because we had the safety net, because we had all of this doing. So here was really one of the early places where we started making architectural changes. In this case, it was the application architecture. And you can make some pretty fundamental changes safely because you have that code safety net. And that's where this started. And then people started to say, you know, this idea of patterns, this is interesting, this is useful. Patterns is actually a way that we as a community communicate with each other about what things work well where. And maybe we can even infer the whys, which is also a very useful thing. And we use those patterns a lot in code, and then we started to say, okay, well, wait a minute. We can take a step back. We can look at the way applications work together to deliver broader functionality by thinking about enterprise integration patterns. We can actually start to think about this from the enterprise level and talk about enterprise architectural patterns. We can start looking at the different possible ways components can communicate with each other, can coordinate their activities, which is fundamentally what you need as you start to have multiple applications working together to solve a problem as opposed to one big monolithic application. So we use the same idea of patterns to say this is how we are going to develop our system. This is much more significant than those earlier revolutions in architecture when we went from everything was a big mainframe application hitting a database. I remember when I first started coding, somebody said there are only 16 programs that ever need to be written. Everything that you do is going to be one of these 16 possible patterns. Obviously, that's not true anymore. Things really started to change radically when we went to this stupendous thing called the client-server architecture, where you started to have servers and clients, and you started to have to think about how are they going to communicate with each other, how are they going to coordinate their activities. And this, when we start looking at things like microservices, we've taken this to the next level of scale in this collaboration. But we're using this same idea. We're using this idea of a pattern. And once you have a pattern, you can step back from that pattern and say, okay, this is the pattern I currently have, and I want to move to this pattern. What does that look like? How can I change what I have right now that is using this pattern into the next? And so I'm moving my ability to evolve my application, not just from the application architecture, but now the communication architecture, the way it interacts with each other, the way those components interact with each other. So what was the next big one? Having been involved in Agile for as long as I have, I often see the arc as how Agile went to different roles. And of course, it started with developers. And I heard many people say, well, Agile's wonderful for developers, but I'm a business analyst, and I have to look at the broad spectrum of the problem. I have to do all of my analysis up front, and then they can chunk it up into little pieces to do their development. And then analysts started realizing that they were falling into a trap that they didn't have to be in, that they could, in fact, specify a happy path and start to elaborate on those use cases and seeing other things. And of course, you had the testers who would say, how on earth can I test an application until it's all written? Because I'm just going to have to run these tests all over again. And you say, well, why don't you automate the simple ones and spend your time doing more exploratory testing, and you can have the automated suite repeat that information. And then we got to the DBAs. And in many organizations, even before the advent of big data, the data that an organization had was an incredibly valuable resource. And the DBAs, quite rightly, took the protection of that asset very seriously. And what that meant is that those databases were in vaults. And you had to go and you had to make nice with the DBA and beg them to make whatever change to the database you needed to make. And of course, because of all the performance characteristics and the safety of the data and all of these things, you can't change a database once it goes into production. You know, this is a major undertaking if you're going to change a production database. And a big part of that, a big part of why it's so hard to change a production database, is data migration. Data migration, conceptually, is easy. You have data formatted this way, and it needs to be formatted that way, and so you copy it over into the new format. Conceptually, it's simple. It's never simple. Data migrations are always messy. And so these DBAs, whose job it was to protect this data asset, of course, they're going to say, you don't change that data. You don't do a data migration unless you absolutely positively have to, which means I'm going to have to design my data model up front, figuring out all the different possible things that could happen in this database. And then the Refactoring Databases book came along, and they took the same approach. What are the patterns? What are the low-level patterns that we can identify in the way relational databases are changed? And rather than doing one massive change to a database, I'm going to break that massive change up into a series of very small changes. And each one of these changes is a change to the database, a change to the code that's used to access the data, and most importantly, it's the migration for just that part of the change. So you have a triple. And now you can test each of the individual component changes, including their migrations. And so when you have this magic field that for 5 years was used for something completely different, even though the name says it's a store code, it's actually some kind of regulatory reference number for particular SKUs that triggers some additional process. And yes, things like that happen because you can't change the database. So you made up these magic fields that did weird things in certain situations. And it's those kinds of things that make data migrations hard. And so by doing exactly the same thing that we had done with code, why do we do a continuous integration? We do it so you've got the smallest possible set of changes so that when something breaks, you don't have a list of 4,000 things to check. You have a list of 5 things to check. We're doing the same thing with database migration. And all of a sudden, what was genuinely hard, getting data migrations right, which was therefore a barrier to being able to evolve your data architecture, to evolve your data representation and your data model, we took that away, again, by using patterns. By decomposing these things into very small changes, and you compose that series of small changes together, and you have a massive change to your database. And then we could eventually check DBAs off the list of people who now understood there is, in fact, a way that I can chunk these things up. And once you have that, once you have the ability to iterate on things, you have the ability to change. You have the ability to evolve your architecture. So that was really the next step in this evolution of how we can think about changing things that are pretty fundamental. Now, the book that was written was based on changes to a relational database, but the concepts apply even if you're looking at graph databases, document databases, et cetera. The specific patterns will change because the way that you change those database representations are very different, but fundamentally, the concept applies. You identify the series of small changes that you can make in that database. You think about how that's going to affect data migrations, and then when you are looking at some change you have to make to your NoSQL representation, you decompose it into these small changes and go. So that was really the next stage. And we're still in about the early 2000s here in terms of the intellectual development. And then came the savior of us all, service-oriented architectures. They were going to save us from all of these problems. And conceptually, there's nothing wrong with thinking about services. And in fact, one of the things, one of the positive outcomes from looking at service-oriented architectures is the fact that people really started to think about you might have separate data stores. They really started to think about the fact that I don't need one big monolithic application. I can have things, I can have smaller scale components. We had flirted with this in the Corba days, but SOA is the first time that people really started to take this serious within enterprise applications. And we had our discussions on SOAP versus REST and what kind, should we use WSDLs or not, and lots of different debates about that. But fundamentally, what was driving people to adopt these architectures was the fact that if we got the granularity right on these things, it would allow businesses to change their fundamental business processes and change the enterprise systems more readily to support those new processes. And that's fundamentally what we were trying to do with SOAP and REST, and with SOA in general, was to say, rather than codifying in one big monolith all of my business processes, which means now my business is stuck. Because even though the business would like to think that they're in charge, what's actually in charge is the system that's running all of those processes. And if I can't change that system, I can't change the processes. And so this is where we started to turn that around and say, okay, I'm going to look at the architecture of my fundamental business systems, and I'm going to start to decompose these into things that make sense from a business perspective, so I can start to change and evolve my processes to meet the changing needs of my customers. So again, this is getting into application architecture, integration, communication architecture, enterprise architecture patterns. And this was another technological step, as well as a mental shift, and people starting to think differently about how they were going to write code to deliver the behavior that the business was looking to achieve. Next big enabler, continuous delivery. The first thing I want to say about continuous delivery is I see it as primarily a risk mitigation technique. Having been up at 3 o'clock on a Sunday morning trying to install something into production, being as careful as you possibly can and still knowing that you're going to get something wrong regardless of how detailed and how thorough the playbook is for install. Continuous delivery done right means that a computer which doesn't make a mistake at 3 o'clock in the morning any more or less frequently than it makes it at 10 a.m. on a Thursday. That, to me, is the fundamental benefit we get from continuous delivery. Oh, yes, it enables all of these other things, but when you look at it from the perspective of a traditional enterprise architect, in a traditional setting with an enterprise that has the DBAs that are protecting their data and that have billions at stake if some of these system deploys don't go right, fundamentally continuous delivery is about making it easier to get something into production. And obviously, if you're going to evolve an architecture, it doesn't do anybody any good unless it's in production. Code has zero value and, in fact, has negative value unless it's in production. Why does it have negative value? Because people are doing something with it. And until it gets into production, it has no positive value whatsoever. And continuous delivery makes it easier and safer and quicker to get code into production. And once you're confident about this, once you're confident about your ability to change your data, once you're confident about your ability to put systems into production, you can start to change things more rapidly. And that's all of what we're trying to do with evolutionary architecture. Now, like some of these other topics, continuous delivery you can have multi-day workshops on. Fundamentally, the basics of continuous delivery is automate everything. You want your configurations to be as standardized as possible. You don't want snowflake servers. If you have a database server, you want to know what it looks like. You want to know that you can destroy it and rebuild it and get it exactly right. Part of why you have to do this is if you're going to be deploying these things into production a lot, you can't have people over on the side mucking and tweaking an architecture. You also have to be able to know as quickly as possible why something went wrong. And if you can't reproduce a problem because you don't exactly know what the production configuration is, or there's no machine anywhere in your organization that has exactly that configuration, how are you supposed to debug it? How are you supposed to know what goes wrong? And so you standardize to the extent you can the deployment, the configuration of your environments, and you automate that deployment. Even if it's a nice, beautiful drag and drop wizard, if you're doing it at 3 o'clock on a Sunday morning, you're going to get something wrong. It is just going to happen. And so you want to be able to automate the configuration of all of these different applications. You want to automate the wiring up of all of these different applications so you know that they're talking to the right instances of things. What's the next thing you want to automate? You want to automate the functionality testing. You want to know that when you deploy something, you have a smoke test that you can run across it to make sure that it's actually deployed properly. If you're going to be changing your production systems regularly, you're going to want to have significant functional tests that tell you, do these systems do what I want it to do? So what we're doing in continuous delivery is marrying together the notion of continuous integration, the emphasis that we've put on automated tests at all levels, and the automation of configuration, treating infrastructure as code, actually checking in your machine configurations. All of these aspects of continuous delivery then allow us to say, now I can safely put this into production. And if we've got the proper pipeline and we've got the proper test environments, this also then provides the basis for making more of these fundamental architectural changes. I want to change my database supplier. I want to go to an open source database. How will I do that? I will practice that data migration. I will practice installing that different database product, which maybe my ops team has never worked with before. That will be rehearsed as that system is sent through the deployment pipeline. I can make some of these fundamental architectural changes and know exactly what's going to happen because it's all scripted. And I've done it first in a test environment, and then in my integration environment, and then in my staging environment, et cetera. So continuous delivery is the process then that allows us to think and deploy into production and to be able to iterate these changes. So if deployment is risky, which it is, people want lots and lots of value in the thing that's going to be deployed, so it makes taking the risk worthwhile. By reducing the risk, you can reduce the scale of the changes, which makes them safer from the perspective of a development organization, and it also makes it more responsive. Because if you have to get a change out, your competitor has just released something and he's eating your lunch, you can very quickly get just that feature out and know that you won't take the entire system down. So continuous delivery is the next enabler. And I actually believe that one of the reasons architecture is now getting much more attention, and you'll see more conferences about architecture. O'Reilly is having architecture conferences now in multiple places. More and more people are talking about architecture. And I think part of the reason they're talking about it is now you can conceive of actually being more creative with architecture. For so long, architecture has been seen as a constraint. It's the evil architects who are telling you you have to do things this way. And that's not the case any longer. And I think continuous delivery is part of that. We couldn't really do microservices well without continuous delivery. And microservices is one of the more significant architectural innovations that have happened in quite some time. And that wouldn't have been possible without continuous delivery. So let's bring it back to evolutionary architecture, and I'll go into more detail with this afternoon, but I do want to talk a little bit about the why. When people first started thinking about architecture back in the olden days before fire, there were relatively static things that people were trying to do. And so you didn't have to worry about changing things very often or very quickly because people were just thrilled to get anything. The automation that was happening early on was so significant that that they didn't care how long they had to wait. They also didn't care how bad the user interface was. And it's only been recently, for example, that some of the airlines have finally gotten out of these bizarre systems. And if you ever saw the cheat sheets that the gate agents used to figure out how to do things like change seat assignments, it was awful, absolutely awful. You could never now get away with releasing software that had as bad a user interface as many of these systems did for years. And why is that? Because everybody has something like this or something like this. And our expectations as individuals are now influencing even what we are willing to accept in our jobs. We want things that are responsive. We want things that are easy to use. And as soon as somebody releases something in the consumer space, all of a sudden, everybody thinks systems like PeopleSoft ought to have a reasonable interface too. Should be easy to use and should be mobile friendly and be able to use it on all the different kinds of devices. So the innovation that is happening in the consumer space is putting pressure even on traditional enterprises to make changes more quickly than they ever had to make them before. And so they can't any longer say, I will release this in 3 years. They can't even say, I will release this in 18 months. And it used to be 18 months was really fast to get a system out. Now, if you can't, we have customers that if you can't conceive of a way to do something in 90 days, they don't want to hear it. 90 days is the outer limit of a development cycle for many enterprises now. 90 days wouldn't have even gotten you through the first gate. That's how rapidly systems now have to be developed. And all of the assumptions that we used to make about how we should do things have to change in that cycle, and evolutionary architecture is a big part of that. Because fundamentally, the job of the chief architect of an organization is to protect the enterprise asset value of that organization. Just like the DBA was responsible for protecting the data, that architect is responsible for protecting the IT assets. And oh, by the way, there are very few companies now that aren't IT companies. They might sell insurance. They might make cars, but they're all IT companies. And so architects are supposed to protect that asset, but they have to protect that asset by allowing it to change. And so the techniques that we've been talking about today, being able to refactor your database schema, using patterns to think about not just application architecture, but communication patterns, the critical role of coupling. You'll hear lots of people say loose coupling, loose coupling, loose coupling. Yes, the looser the coupling, the easier it is to change things. But some things have to be coupled. Maybe it's a semantic coupling because they have to communicate. Or maybe it's for performance reasons. Maybe you would love to have these things all in different processes, in different places, but you've got to get throughput that isn't going to allow you to do that. Coupling is now something that we can talk about as a first-class citizen, along with things like maintainability and reliability and time to recovery and all of those different ilities that architects used to worry about. And I would maintain that we actually have evolvability now as one of those fundamental architectural ilities that we need to think about. Along with being maintainable, along with being able to recover a system, auditability, security, all of those different things, evolvability is now a first-class citizen of an architecture, and that's something that we are going to continue to see new techniques arise. We're going to, I think, continue to see new innovations in architecture like microservices because we have not only more possibilities, but we're also seeing different kinds of problems and different expectations from the people who use our applications. And so we're going to have to continue to evolve our thinking about how we build those systems. And that does include architecture. So thank you very much.